Swayam Prabha. Digital India. Educated India.
In this lecture, I am going to introduce the analytical dynamics formulation using the analytical mechanics developed by Lagrange. We will look at the introduction to analytical dynamics, define what is the configuration space of a dynamical system, define the generalized coordinates to represent the configuration of a dynamical system, and talk a little bit about constraints. It was known since quite long that light minimizes the time it takes to travel from one point to another. This is known as Fermat's principle, and it was known since 1662. The question naturally arises, can there be such a minimization principle for a dynamical system? Can we say that when a dynamical system evolves, something is minimized or maximized, extremized? Can we say something like this, or can we formulate our motion of the or the dynamics of a system in terms of some minimization or some maximization, some extremization, just like light minimizes time it takes to travel. So, can there be such a minimization or extremization principle? This was answered by the analytical mechanics formulation by Joseph Louis Lagrange, and this was done around 1788-89. It was in 2 volumes that Lagrange published his magnum opus, which had the title Mécanique analytique, and from here started the formulation of analytical mechanics or analytical dynamics. Now, this was based on variational calculus. So, finding out dynamical paths, that means the path followed by a dynamical system, finding out dynamical paths that extremize some global quantity, some quantity just like light minimizes time. So, similarly, can we find out dynamical paths that extremize some global quantity? Now, how do I define paths of a dynamical system? For example, a particle, if I take a particle, then path of a particle is how the x, y, z coordinates of the particle is changing in the 3-dimensional space. How is it changing? That is a path. In a rotating body, a rigid body, let us say, then its motion of the center of mass and its orientation, change in orientation, and now we have already discussed how orientation can be represented as paths, let us say on spheres or within spheres, for example using Euler parameters or axis angle representation. Therefore, there also we can think about some paths, but suppose it is a more general thing, it is combination of a number of bodies, or there are constraints. How do we define paths, or how do you define the configuration of a complicated system? So, we will start by discussing what is known as the configuration space of a dynamical system, and this can be very general. I mean, it need not necessarily be some coordinate, it can be for example, in thermodynamic systems coordinates can be temperature or pressure, these can be coordinates, and you can formulate things in terms of this what is known as the configuration space and the configurational space coordinates. So, what is a configuration space? Configuration space is a space in which a point fixes the configuration of a dynamical system. So, in this space, configuration of a dynamical system is represented by a point, just like position of a particle is represented by a point in x y z coordinate system. So, x y z coordinates are actually the configuration space of a particle's motion. We have discussed orientation, we have discussed parameterization of orientation. A point in the 4-dimensional space can represent orientation of a body. Therefore, the orientational coordinate or the configuration space of the orientation of a rigid body is a point in this 4-dimensional space and on a unit sphere. This was the Euler parameters, the space of Euler parameters, the 4-dimensional space. Therefore, the configuration space in which a dynamical system evolves is a space in which a point represents complete configuration of or fixes, this point fixes the configuration of the dynamical system. Every point in the configuration space is specified by a set of what are known as generalized coordinates. Just like x, y, z specifies the location of a particle, so x, y, z are the generalized coordinates for the particle, and the space is the 3-dimensional Cartesian space, that is the configuration space, and the generalized coordinates are x, y, z. So, these coordinates uniquely represent the configuration of the system. Where is it located, how is it located, everything will be answered by the generalized coordinates. The formal definition of generalized coordinates is given here. The minimum number of independent variables required to uniquely fix the configuration of a dynamical system. Therefore, this is a minimum number, this is very important to note, minimum number of independent variables required to uniquely fix the configuration of a dynamical system. Change in the generalized coordinates is governed by the dynamics, the laws of motion, and represented by a dynamical path in the configuration space. Just like orientation, we have discussed orientation using Euler parameters. There are 4 Euler parameters E0, E1, E2, E3, and these are these 4 parameters represent a point on a 3 sphere, and as the orientation changes, these parameters will change, but it will always remain on this 3 sphere, and therefore, as the system evolves, the generalized coordinates are going to evolve, and they will be governed by the laws of dynamics. Let us look at some examples. A point in a plane, it is represented by the x and y coordinates in the Cartesian space, in a 2-dimensional Cartesian plane. Just by x and y we can locate a point, and all this 2-dimensional geometry that we have learned, everything uses this 2-dimensional Cartesian plane, and a point in a plane is represented by these 2 coordinates. Therefore, the generalized coordinates are x y, and the configuration space is this x y plane, the generalized coordinates. So, x y, first of all, there are physical coordinates which gives us this notion. In the physical world, we are looking at this x y which we can measure, for example, but the generalized coordinates in this case are also x y. We can measure these generalized coordinates, but not in every system can we possibly measure. Physical coordinates we can always measure, but generalized coordinates are abstract coordinates usually, which from where I can always map to the physical coordinates, and the generalized coordinates are the minimum number of such coordinates which can completely specify all physical coordinates of the system. Therefore, the configuration space of a point in a plane, in the x y plane, is R2. So, R cross R. So, 2 real lines, oriented in this manner, I can represent location of any point in a plane. We have 2 degrees of freedom. What we say is we have 2 degrees of freedom. We can choose 2 things to completely fix a point in a plane. Number of generalized coordinates give us the number of degrees of freedom of the system. We can choose this x and y independently of one another. Therefore, we have 2 choices, and that will completely fix the point in the xy plane. Let us now look at a pendulum. The bob, which is the particle, is moving in the xy plane. I can measure these xy coordinates, but then there is a constraint. These 2 xy these coordinates are not independent. I cannot arbitrarily specify these xy coordinates of the bob. And the constraint is x square plus y square is equals to L square, the length of the string. L is the length of the string. xy are the physical coordinates. xy are the physical coordinates which I can measure and see in the physical world. But I can represent these xy in terms of another coordinate, which is theta, the angular coordinate, which also in this particular case I can measure. And therefore, the configuration space, which will not have any constraints, is only represented by this theta. So, the configuration space in the case of a pendulum has only theta as the coordinate. So, theta is the only coordinate in the configuration space. Therefore, we have 1 degree of freedom. This system has 1 degree of freedom. And the configuration space in this situation, in this example, is interesting, because theta is a periodic thing. Theta and theta plus 2 pi are the same things. There is a periodicity. When theta goes from 0 to 2 pi, it comes back to 0. Therefore, it is a circle. The configuration space of a pendulum is a circle, which is written as S1. It is 1 dimensional sphere, it is S1. And theta is this configurational coordinate that has been indicated in this figure. This theta is the configurational coordinate. If I am given theta, I can locate the pendulum. Of course, I must know the length. I can locate the pendulum if I know theta and from where theta is being measured or defined. So, I can locate the pendulum. Therefore, the generalized coordinate is only theta, and we have 1 dimensional configuration space. The degree of freedom of this system is 1. Now, we look at a car in a plane. This is a very common example. How do you locate a car in a plane? We have some point on the car, its location in the plane, x y is the location of that point, and the orientation of the car in the plane. So, theta is the orientation of that car in the plane. These are physical coordinates that we normally see or visualize or measure, but these are also the generalized coordinates. But you see, there is a very special thing about the car. A car in the generalized coordinate x y theta, if I represent x y theta like this, I have done in this figure, I can think of points in this x y theta space, x y theta space, which is the configuration space, and because again theta is 2 pi periodic, therefore, this configuration space is R2 cross S1. Now, imagine points in this configuration space. Now, as I have mentioned, any point represents the completely fixes the configuration of the system. For example, this point A, which is at theta equal to 0 at a certain location x y, and this point B, which has a certain theta value and another x prime y prime, let us say. Can I join A B by any path? Can I join A B by any path? So, suppose a straight line path. Can the car move in this path? Let us say B is just vertically above A. That means, on this green path x y location of the car is not changing, but the car is being rotated, theta is changing, but x y is not changing. Is that feasible? That is not feasible. Though the points represent the configuration all right, but arbitrary paths may not be possible, because there is a rolling constraint, the car cannot slide sideways. There can be dynamical paths which are specially which satisfy certain constraints which the car has to satisfy. It can roll, the wheels can roll, but wheels cannot slide sideways. So, there is a difference between dynamical path and any path in the configuration space. Arbitrary paths cannot possibly be connected in systems where there are these kinds of constraints. We are going to discuss this a little later. The degree of freedom of the car is 3, because I can take the car anywhere x y and I can keep it oriented in any direction. I have to be able to drive it properly. Therefore, I can take it to any place and in any orientation. There are constraints on the motion direction. There are admissible or dynamical paths which must respect these constraints. Let us look at this conical pendulum. This is pendulum which also has a rotation, spin about the y axis, which is vertically upwards. The location of the bob, the physical coordinates of the bob are x, y, z, but x, y, z must satisfy this constraint, x square plus y square plus z square must be equal to L square. In the physical space, therefore, we have a constraint, but I can represent the x, y, z in terms of two angles, theta and phi, which I have indicated. Theta is the angle made by the string with the y axis, and phi is the angle made by this radial line which goes to this point which is vertically above the bob, and this angle measured from the x axis is phi. I can represent the location x, y, z of the bob in terms of only theta and phi, and I have done this. Therefore, our configuration space for the conical pendulum is only theta phi. With this theta phi, I can find out x, y, z of the bob. Now, the generalized coordinates are theta and phi. Let us look at the configuration space. We may think that the configuration space is R2, we can move, of course, we can move phi from minus infinity to plus infinity, theta from minus infinity to plus infinity, but there is a periodicity. When phi goes to 2 pi, it is same as 0, phi equal to 0. Similarly, when theta is pi and theta is minus pi, is the same configuration. Therefore, these opposite sides are identified. This side, this whole side is identified with this side. Therefore, I can roll it to form a cylinder. In the first instant, I can roll it to form a cylinder. There will be a joining point, because this side and this side, these two sides are same. I have rolled this thing to form this cylinder, and this side and this side are also the same. Minus pi, theta equal to minus pi and theta equal to pi are also same. Therefore, this side and this side, they are also identified. Therefore, I can twist and join them, and what I get is a torus, a 2 torus, and theta and phi can be thought of as angles being measured like this, theta and phi. Therefore, the configuration space of a conical pendulum is T2, the 2 torus. It is a donut shaped object, and the degree of freedom of a conical pendulum is 2. Let us look at a bead on a rotating circular hoop. This is a circular hoop on which a bead can slide, and this hoop is rotating at a constant angular velocity omega. The location of the bead can be represented by x, y, z, but then there is a constraint that x square plus y square plus z square is the radius square, and radius of what? Radius of this hoop. And if you think about it, as this hoop is rotating, the bead can actually move on a surface of a sphere. X, y, z can be represented like this. What are theta and the other angle, which is omega t? So, theta is this angle being measured from the z axis, and what is omega t? Omega t is the rotation angle. This rotation angle is omega t. Therefore, the x coordinate I can find out by projecting this line in this direction and taking a projection on the x axis. So, this is x, this is y, and z is obtained as minus r cosine theta. This is not very difficult. Therefore, the complete configuration of this bead can be represented only by theta. Of course, time will also be very important. Time will also be very important, because that will tell us how much the hoop has rotated, but the configuration space is represented by only theta. I can locate the bead. I will need the time as well, of course. The configuration space is S1. Generalized coordinates only theta, and therefore, we have only one degree of freedom. We do not have any control on time, even though we require that time to exactly locate the bead, but time is not a coordinate which we can fix. So, therefore, degree of freedom of this system is 1. Let us look at a pendulum on a cart as shown in this figure, and this cart is freely moving on a frictionless surface. We need these two coordinates x and theta to locate the bead as well as the cart. So, these are the physical coordinates, and they are also the generalized coordinates. X and theta are also the generalized coordinates. Now, x is the real line. I can have any x, forget about any abstraction. I can theoretically I can go from minus infinity to plus infinity in the x direction, and in the theta direction minus pi and plus pi are identified. Therefore, we have a configuration space which is r cross s, which is a cylinder. We have 2 degrees of freedom. I can locate the whole system by fixing x and theta. Then I will know the location of the cart as well as the pendulum. Let us look at now this example of a pendulum on a cart with the cart's motion being specified as a function of time. U t, which is the motion of the cart specified as a function of time. the physical coordinates definitely are still x and theta, but then I have a constraint. The constraint is x minus u t must be 0. In other words, x must be equal to u t. Therefore, there is a constraint. The constraint is x minus u t is equal to 0 and x must be equal to u t. Therefore, theta is the only generalized coordinate and the configuration space is S 1. Degree of freedom is 1. I have only the freedom to specify theta. The motion of the cart is specified in another way in terms of time. Now, configuration space of a rolling coin. Now, this is a complicated example. Consider a rolling coin as I have drawn here. It is in contact with the ground. Ground is the xy plane. It is in contact with the ground and always will be in contact with the ground, and that ground contact point is indicated as C, and it is moving on a certain path shown by the green curve on the ground. At this position, at this instant of time, let us say that the direction of motion of the coin makes an angle psi with the x axis. Therefore, the direction of motion of the coin makes an angle psi with the x axis. Let us define a coordinate frame direction which is perpendicular to the face of the coin, which is a very natural choice and passes through the center of mass G of the coin. Another coordinate axis which is parallel to the direction of current motion and which is horizontal. Therefore, this x prime axis is parallel to the, or it is absolutely horizontal. That means, this x prime axis will have no projection on the z. In other words, x prime, this frame direction will have no projection on the vertical z that I have drawn, or the dot product of x prime unit vector with z unit vector z cap will be 0. Therefore, x prime is perpendicular to the z axis and it passes through G, and x prime also lies on the face of the coin. X prime also lies on the face of the coin, and I define a z prime axis which completes the right handed coordinate system x prime, y prime, z prime. Y prime I have not written, just for making the figure clear. Y prime is the normal to the coin face passing through G, and x prime is perpendicular to the vertical direction. That means, x prime cap dot z cap is 0. It is perpendicular to the z axis, the ground fixed z axis, and also lies on the plane of the coin, and z prime of course lies on the plane of the coin. We have fixed the axis, we have fixed one direction, that is psi. The coin is of course spinning, and therefore, this spin angular velocity will be about y prime. The spin angular velocity will be about y prime. There is one more orientation, and that is the tilt of the coin, that is measured again from the z axis, which is fixed to the ground, which is vertical. The z axis, the angle between the z axis and z prime axis about x prime axis. The rotation phi is about the x prime axis. The angle between z axis and the z prime axis measured about the x prime axis, that rotation is phi. In other words, the rate at which, let us say, phi is changing, the rate at which the tilt of the coin is changing is measured about x prime. Now, the coordinates that will represent the physical coordinates. The center of mass, of course, x g, y g, z z, right. So, the center of mass x g, y g, z g, and the orientation can be represented by psi, which is the angle made by the direction of instantaneous direction of motion of the coin and the x axis as shown in the figure psi, and phi is the tilt of the coin. Psi and phi together tells us about the orientation, and theta is about the y prime axis, which tells us about the spin of the coin, and I have indicated theta in the figure. Theta is the spin angle of the coin. Now, the constraints, there are of course constraints. Can you arbitrarily fix x g, y g, z g? You cannot, because the coin must always be on the ground. Therefore, the z g coordinate can always be written in terms of the radius of the coin and the tilt of the coin. This is very simple to see from the figure, that z g must be equal to r cos phi, and at phi equal to 0 you can see that z g is r. Phi equal to 0 means the coin is upright, and phi is equals to pi by 2, that means coin is on the ground, then z g is 0. Then comes a very important constraint, the no slip constraint. This we have to work on. No slip, at the contact point C there is no slip, there is no relative velocity of the coin particles and the corresponding contacting ground particle. The relative velocity must be 0. Now, to look at that no slip condition, we must start by looking at the angular velocity of the coin. Angular velocity omega in the primed frame x prime, y prime, z prime. How do we represent that? We have been doing this for quite some time now. First of all is the spin theta dot, which is about the y prime, this is the y prime axis. Theta dot about y prime axis is theta dot j prime cap. Then the rate of change of tilt, which is phi dot taking place about the x prime axis. Therefore, phi dot I prime cap, and psi dot the change of this, which means the change of direction of motion of the coin. So, this is psi dot, the rate at which psi is changing is psi dot, and that is about the z axis really. The rate of change of direction of the motion of the coin is about the z, and that z unit vector z cap I have represented in x prime, y prime, z prime. It is very simple to represent, cosine phi k cap plus sin phi j cap, because remember this is nothing but z cap. So, representation of z cap in x prime, y prime, z prime. Now, velocity of that contact point in this x prime, y prime, z prime frame V c prime is V g prime plus omega cross this minus r k prime cap, is the velocity of the center of mass plus omega cross g c. This is nothing but the vector g c, everything in that primed frame. Velocity of the contact point therefore is velocity of center of mass plus omega cross the vector g c, and write every vector in the primed frame and you will get this velocity of contact point, and that must be 0, absolute velocity of contact point must be 0. This is the no slip condition at contact point, and therefore, we start writing these velocities in the primed frame. This is the representation of V g in the primed frame, plus if you look at, if you take this omega cross this minus r k cap prime, you will get this condition finally. And if you look at the components, these are the components that must be 0, because the whole vector must vanish. Therefore, the components must vanish. I will leave it to you to get this final expression. Now, we are going to represent this in the XYZ frame, which is the fixed frame. For that, I will need the rotation matrix. The rotation matrix between x prime, y prime, z prime and x y z. I want to find out the rotation matrix from x prime, y prime, z prime to x y z. How can I get the x prime, y prime, z prime? So, that is the question that we will ask. Initially, suppose x prime, y prime, z prime were coincident here. How do I get to this current configuration? First is I rotate about z by an angle psi. I rotate by an angle psi about z axis. So, z about psi, then I get a frame which is like this, which is rotated. So, this here goes x prime, here goes y prime, and z prime is coincident with z still. Then the tilt about the new x prime, I must give a tilt of angle phi, and these two rotations are rotations given in this order are about the new frame. I get the first frame by rotating about z by an angle psi, and then about the new angle x axis I give the next rotation of phi, which gives me the tilt. And since it is taking place in the new frames, I post multiply this sequence to obtain the rotation matrix. This is the fundamental rotation matrix of psi about z and fundamental rotation matrix of phi about x prime. If I take the product, this is the net rotation matrix. This is our net rotation matrix. Now, velocity of the center of mass in the XYZ frame can be transformed using this rotation matrix. This is a vector, velocity of center of mass is a vector, and that has a representation in the prime frame as well as in the ground fixed frame. The rotation matrix that we have written out gives me a transformation from the primed frame to the ground frame. Therefore, if I multiply with the velocity in the prime frame, I will get velocity in the ground fixed frame, velocity of the center of mass. Or I can write velocity of in the prime frame as R transpose. This is inverse. Inverse is transpose of the rotation matrix times the velocity in the ground fixed frame. Now, velocity in the primed frame can therefore be written as just multiplying this by x g dot, y g dot and z g dot. This is in the ground fixed frame. This velocity is in the no, not in this matrix, but the transpose matrix. We have to multiply with the transpose matrix. This V g is nothing but x g dot, y g dot and z g dot. This is V g, and we can obtain V g prime, velocity in the primed frame, and that is what I have written out here. And remember, we had these constraints in the primed frame, the no slip constraint in the primed frame, and therefore, I have V g x prime is this, and from the transformation I have this. Therefore, this must be equal to this, and similarly I can write about the other components and finally get the constraints in terms of velocity of the center of mass as seen from the ground fixed frame, rather than velocity of the center of mass represented in the primed frame, because it is inconvenient. It is inconvenient to represent the velocity vector in the primed frame, which is the moving frame. It is always much better to write in terms of velocity measured in a ground fixed frame. We get these three constraint equations, of which if you use this contact point constraint, that Zg, this Zg is equals to r cos phi, then you will find that this second and the third equations, they are actually dependent, they are not independent, and therefore, we have only two independent constraints which represent no slip condition. These constraints are non-integrable constraints, they are also called non-holonomic constraints. These two constraints are, they represent the no slip condition. Therefore, finally, let us get back to our initial slide on this. We had the ground contact constraint, which is a holonomic, which is a constraint in terms of the coordinates, and we have these constraints which are in terms of derivatives of the coordinates, and they cannot be integrated. I cannot get a constraint in terms of the coordinates from these two constraints. They cannot be integrated, they are called non-holonomic constraints. Therefore, we have one holonomic constraint in terms of coordinates and two non-holonomic constraints here, but then we can replace this. In other words, Zg is not really, I mean that is a physical coordinate, no doubt, but generalized coordinates can be xg, yg, psi, phi and theta. Using phi and r, I can calculate Zg, that constraint I have. Therefore, we have only 5 degrees of freedom for a coin rolling on the ground. To summarize, we have introduced analytical dynamics, we have looked at configuration space, which represents the configuration, which fixes the configuration of a dynamical system using the generalized coordinates, and we have looked at some examples and constraints. With that, I will close this lecture.